My screen is visible, right?
Yes, ma'am.
Yes,
Yeah.
yes.
Okay. Okay. So, in the previous class, we were talking about KNN algorithm. Okay, and I think we mentioned about different variations, etc. Okay, but we have tried numerically only our basic KNN algorithm, K nearest neighbor. That's what our KNN is. And there was a query, like usually, I mentioned that usually we choose odd numbers of K so that to avoid kind of tie, okay, but still we may have tie, like say for example Vishnu was mentioning that day, say K equal to 3, okay, so it's still odd, but maybe our third, fourth and fifth distance are same, okay, so then even if I say K equal to 3, fourth and fifth distance are also same as K equal to 3. So that was his question. So still there is a like, how do we choose? So maybe we have three distances in that same, like we have for the query instance, we have three neighbors which have same distance, okay, and we are using our basic KNN. Okay, so we have a kind of tie issue, or we don't know what to choose if we have multiple classes, and then altogether if it's not coming it as one majority, then how do we choose? Or when we have same like K equal to 3 and then we have third, fourth and fifth neighbors as same distance, now whether to choose three neighbors only or fourth, fifth also to be considered, etc., are a confusion. Now you have to understand this KNN is not very strict model, okay, it is like just based on this idea of finding out the nearest neighbors and predicting based on what our nearest majority of the nearest neighbors are telling of the particular query instance. That's all the model says. Okay, so now there are different suggestions given. Okay, as such we will not see any specific case in our books or something, but when I read through, there are suggestions, like one is like what we said in the previous class, we can have a weighted approach, weighted KNN, where the closest neighbors are given more weightage. Okay, so there may be of course a difference, but still if you have this kind of situation where K equal to 3, 4, 5, this solution, this may not solve that because our K is 3 and we have say 2, 3 neighbors after that which are having the same distance, so we don't know whether to choose. So suggestions are basically you can either choose randomly the just the third in the row, so the third neighbor alone, or we can actually like randomly select one of these, because we have told three neighbors but we have actually two more neighbors which have the same distance. So you can either choose only K equal to 3, so only three neighbors, or suggestion is as we have nearest neighbors more than that, we can include all the five. So that also is one suggestion. Plus, to avoid such conditions, we can have other ways to handle, like say for example, weighted or other approaches. But anyways, when such cases happen, we cannot always tell that this is the best approach or we should do like this. So there is nothing like a hard and fast rule. Like if you have more neighbors with same distance, because that becomes a specific case of your data, isn't it? So if you feel there are many neighbors which are having same distance to the query instance, we need to have a modification in the algorithm, like say we need to choose the sample randomly, uh, whichever, like if you have three neighbors which have same distance, we need to choose one of them, or we need to choose all of them. So all these are possibilities. Okay, and then take the majority. So that is like a variation and suggestions. It is depending on what you feel or what how your model is performing when you do that. So based on that you can actually decide based on your data how it is working. So there is no like specific rule of how you can handle it. I did not see anything very specific. They are telling to even to change the value of K. Okay, so keep on modifying your K so that you get a proper majority. Okay, instead of having a tie kind of situation. So these are all different suggestions found. Okay, we need to try maybe multiple methods and then conclude. Okay, so that's what I understood from the reading. Okay, so Vishnu, is that fine?
Yes, ma'am. Ma'am,
Okay, yeah,
like a small doubt in
yeah,
this.
yeah,
So
yeah, sure.
you told about weights, no, ma'am,
Yeah,
using
yeah,
the weights version. So even
yes.
in that one, the same issue will come. Like
Yeah,
if
yeah,
the
this
distance
specific
is
issue may not be solved because
okay,
even if you apply weights for the first two instance, your k equal to 3 and you have fourth and fifth instance also with the same. So now that weighted may not solve actually in your case. What is the only possibilities? Either you should have a approach that you will choose only three neighbors. Like in this example, I have k equal to 3. So I will choose only 3. So randomly I will choose, like we have 3, 4 and 5 instances which are actually having the 3, 4 and 5 neighbors actually having the same distance. In that I should be randomly selecting one. That can be one approach, or whenever we have multiple distances same, we need to choose all of those. That also can be another approach. Weighted will not improve in this specific doubt of yours.
yes, ma'am.
Okay.
Thank you.
Okay. So that's all we mentioned about that particular thing. And then we were discussing about KNN, where we have, say, we might have, what is that, discrete values. So then we discussed about, say, for example, color. So we might have an approach where a simple approach could be like, say, we'll find the difference. If the color is same, like we are anyway finding the distance, isn't it? So we don't actually have a distance between color. But an obvious approach could be if the two distance, like if you are comparing first instance and the query instance, that particular attribute when you compare, that is color attribute when you compare, if they are same, you can put the difference as 0. If they are different, you can put the difference as 1. Okay. Or it can be like a sophisticated approach where you have different values for each of your colors, and you might get a different value. Like, say, very close colors would get a smaller distance, and then very different colors would get a large values when you find the difference. So that kind of approach also is possible. Okay, then we talked about what is that? I'm just refreshing what we covered. So then we discussed about our real or continuous value. I mean, in the sense, real valued output variable. If then, how do you use your KNN? So there also, for the k nearest neighbors, we identify the labels. It would be real values. Find the average. That would be our prediction for the unknown tuple. Okay, that is our I mean, that is the way it would be done. Then what about the good value of k? So then we discussed about good value of k would be usually it is not like we'll suddenly say k equal to 5 is the best, nothing like that. We need to vary the parameter k and see which our error rate is minimized. So that's how you will choose. And there are attribute weighting, etc., where we have certain attributes given weighting. That is also there. Instance also, the neighbors also would be given weighting. That approach is there. That is closest neighbors. Like, say, if you find the first 5 neighbors, the first neighbor will get more weightage, the second neighbor will get little lesser weightage, and so on. So when you predict, or when you take the majority, there is a weightage also associated. So the closest neighbor, if it says yes, that has more weightage, kind of thing. So that is different. There is attribute weighting also. That is, the certain attributes also might be given certain weighting. So when you find distance, there would be a difference. And also we mentioned about different, like you need to scale when there are large variation in the values of the attributes. That is because, say, and I mentioned that it is usually there when you have distance-based algorithms. Some, like, say, for example, you have height, which will vary from very small variation in the numbers. But when you have income, it will have, like, say 10,000 to 1 lakh, something like that. So there is a large variation in the value. So, but we have all these parameters in our data set. So when you find the distance, those kind of attributes might actually dominate. So which is actually not sensible. So what you can do is you can scale down to a particular scale, like 0 to 1 or -1 to 1, and then perform the KNN. So those things were discussed. Okay. And then we actually moved on to Bayes theorem. Okay. and then we discussed how Bayes theorem was like we derived it, okay, and then we actually saw a simple example, okay. We didn't solve it, we just saw this example. So here what we discussed was, in this example, it says it is a situation where a patient takes a lab test and the result becomes positive. Now the test returns a correct positive result only 98% of the cases in which the disease is actually present. Okay, and you also told me that positive given cancer. Okay, that is actually 0.98, 98 by 100. So that is 0.98. So now what is 1 minus 0.98? How do we tell that? That is actually our the other part. That is, you know that only in 90 it is having cancer, and only in 98% it came correctly. Okay, the model, I mean the system, the lab test came correctly. Okay, that means the rest of the cases it came negative. So that is actually your minus given cancer. Okay, P of minus given cancer. If you see the right side, the second one is your 1 minus 0.98, that is 0.02. Now what about 97? What is your 97? 0.97 comes here. That is, it is saying that correct negative result in which in cases in which the disease is not present. So disease is not present and the result came correct. That means negative given no cancer. That is 0.97, and no cancer, but then the test was wrong. That is your positive given no cancer. That is your 1 minus 0.97, which is your 0.03. Okay, so these are those values. Okay, and then so if you have tried, you would have got the same. Okay, now how do we find? You know what is Bayes theorem, isn't it? So it is just repeated. So whether given that the lab test, our question was, we observe a new patient for whom the lab test returns a positive result. So given that it is positive result, now we need to tell whether the patient actually has a cancer or not. So how do we say that? This hope you remember this particular notation, H and D. H is your hypothesis or your actual output variable kind of thing. So your Y, and D is your data set. Okay, so you are asked, given the data that is given positive, whether you actually have, I mean the person actually has cancer. So how do you know that? So we have different possibility for your H. Okay, so it can be cancer or it can be no cancer. We need to find the probability of both and take the maximum. So first option is to find, of course your given is already known to you, like it is given that it is a positive result. So given positive, what is the probability of the patient having cancer? That is the first line what you see. Given positive, what is the probability of the patient having no cancer? That is the second line what you see. And how do we write according to our Bayes theorem? See here, if you notice, we are not writing the denominator part because in both the cases it will be the same term and we are just comparing. So why do we have to again divide and see? So we are not doing that. Okay, we are just comparing, so we are just taking the numerator. So first one will be written as P of plus given cancer into P of cancer. So that is calculated as 0.0078. And the next one, these values we got it from the previous explanation what they had given. Now the second line is P of no cancer given plus a given positive result. That is P of positive result given no cancer into P of no cancer. Okay. So when we multiply, we get the appropriate values. Now how do we choose whether the patient, how do we, like, what would be our diagnosis whether the patient is having cancer or not? Of course, we'll tell the patient would be not having cancer because our probability for the no cancer is high. Given that it is positive, patient not having cancer is high. Okay. So we H map your maximum up posteriori or the final prediction kind of thing is no cancer. Okay, so should we diagnose the patient as having cancer or not? We predict or we diagnose them based on this model or the data and our understanding of Bayes theorem. We diagnose the patient is not having cancer. Okay, now same question, okay, with a negative result. Okay, here also if you see in the end it might come like no cancer. Don't think why it is like that, because in most of the cases the patients are having and we are taking only just a base theorem. Okay, it's not actually your naive Bayes classifier, and we don't have multiple attributes, etc. So based on this data and understand, I mean, whatever we can use with the Bayes theorem and existing conditional probabilities, we are trying to figure out. Okay, so how do you find, based on the Bayes theorem, whether the patient has cancer or not, given something like that? You can just consider. So the same example, if the lab test had returned a negative result. Okay, so now how will you write? Given negative, whether the patient has cancer. So that is the first line what you see, P of cancer given no, I mean negative. Same way, P of no cancer given negative. So that is what we are calculating like previous step. And finally we get the patient having given the result as negative, still the patient probability of patient having no cancer, in the sense patient not having a cancer, is high. So our model would predict only no cancer. Okay, even in this. Okay, because most of the cases, that is how our data says. Okay, so it's realistically, don't think like that. You may feel that for positive result also we are telling it is not negative. Not that way. Just understand that we have only that much sufficient, I mean, like very limited information. With that we are telling we'll diagnose it as cancer or not. Okay, anyway, we are not going to use just naive Bayes alone. I mean, in the sense, this is we are not just using Bayes theorem. It is the basis of our naive Bayes classifier, but we have attributes also. We have many attributes to consider. So of course our prediction would be better. Okay. So now let us see what is naive Bayes classifier. So like other classification algorithms, one of the most important practical learning methods. So when we use this, usually when we have large training set or moderate training set, okay, and attributes that describe the instances are conditionally independent given the class. This is the assumption what our naive Bayes makes. We'll see that. So given the class, the attributes are independent. Attributes or features are independent on each other. We'll see what is that. Okay, so attributes are independent of each other given the class. Okay, so we'll just see that. Now that is the assumption made by our naive Bayes. Okay, so of course if you actually see the real case scenario, we may not be always able to say that attributes are independent of each other. So of course there are situations where we have dependency, but for naive Bayes classifier to work, this is the assumption made. Okay, so now mainly in classifying the text documents, etc., and also diagnosis, we have this naive Bayes classifiers. Okay, it doesn't mean that always in all the applications of text classification it might work well, but usually it has been found that it has successfully classified the text documents. Okay, so now this is a supervised learning technique, okay, based on probability theory. Okay, we have compute the probability of instance belonging to, like you have say yes or no, we find the probability of it being yes. We also find the probability of that particular instance being no, and then whichever is maximum we try to classify. Okay, so that is our generic approach of naive Bayes. Okay, so this is the same thing. It is easy, it is simple actually, and works fast. It also performs well in multi-class prediction. Also for the categoric inputs, actually it performs the variables, the attributes. If they are categoric, this performs more better. Okay, so so this is just like when you use and what are the where we have, etc. So let us see what is this classifier. Okay, so see, just because there is a difference in the notation, you don't have to worry. It is very simple. Okay, if you see, I am audible, right?
Yes, ma'am.
Yes, Priyanka, you are very much audible.
Yeah. Okay, thank you. So, so we can say naive Bayes classifier. So when we take, so X is our input, isn't it? And each instance X. So we write the small x, that is our each instance. And for each instance, we'll have attributes. We know that, like say, when I say patient, we know that say height, weight, say blood parameters, your vitals, all that contributes to attributes or features. So they are represented as A1, A2, A3, etc. So for each instance X, we'll have this. Okay, and corresponding, there will be a Y value or an F of X. Okay, or a V value, we can say. Okay, so now how do we find that? Okay, so V map is our maximum a posteriori probability. Okay, so now which is maximum chance, that's what we are saying. So we are trying to find, we have actually written this in some other form, argmax etc. in the previous Bayes theorem also. So here what happens is Vj is like, say if it takes two values, say for example in our previous case, yes or no. Okay, Vj can be yes or no, or Vj can be, say, ham or spam, all that. It can be multi-class also. I'm just telling it's the output variable, set of output variables. Now, given our data set, what is the probability of it being a particular value of V, which is our target variable? Okay. So that is what we are going to find. So we know that from our Bayes theorem, the first equation can be replaced as the second equation, because P of Vj given a1, a2, etc. an can be just replaced as P of a1, a2, an given Vj into P of Vj divided by P of a1, a2, etc. an. This is what our Bayes theorem says. It's the same thing. Okay, now since we are trying to find maximum, okay, we have multiple values of Vj and then we find a maximum of it. See, if you see argmax Vj belonging to V, Vj can be, say, V1 can be yes, V2 can be no, that way. Okay, or say V1 can be cancer, V2 can be no cancer, or V1 can be ham, V2 can be spam. Okay, these are all different values it could take for a particular problem. So for all this we find, and then whatever is the maximum we try to find as our final output. Okay, and then now since we know that we are taking the maximum only, we'll take only the numerator part. So that's why it is written a1, a2, an given Vj into P of Vj. Okay, when you write given Vj, that is your conditional probability. When you just write P of Vj, that is your normal prior probability. Okay, now this is our assumption what we were talking about previously. Okay, so previously we told name Bayes makes an assumption that given the class, okay, the attributes are independent of each other. Okay, so the first terms become the first term, like you have just before this assumption, if you see that the line, okay, this argmax of P of a1, a2 till an given Vj into P of Vj. That's what is our final statement now what we have made, isn't it? So the first term, that is a1, a2, etc. an given Vj. How do we write that? Because we have an assumption telling that given Vj, that is given the class, the attributes are independent of each other. That's the assumption. Okay. Now, if that is the assumption, then we can write, we just multiply them. Okay. So P of, so then we can just write this as P of a1 given Vj into P of a2 given Vj into P of a3 given Vj, etc. That's what is summarized as pi I. So each I would be your a1, a2, a3, etc., which are your attributes. A is your attributes, V is your corresponding Y value or your output variable. Okay. So that is how you will consider your P of this particular term. Okay, because you are taking an assumption that given the class, your attributes are independent of each other. Of course, you may have a doubt that in real case scenario, it may not be like that. That is there, but we are not considering that. We assume that given the class value or the class label, we assume the attributes to be independent of each other. Okay, so now since we have made that assumption, now our classifier looks like V and B, that is our output value, the target value using our naive Bayes classifier is argmax of P of Vj into pi I P of Ai given Vj, that is our attributes, conditional probability for all our attributes for that particular class. So given Vj, so say for we'll see the example anyways. Okay, don't so much worry about this terminology and all. I'm just telling because if you see, you should understand. That's all. So our target, given the class label, each attribute's probability, the conditional probability, multiply together, and the probability, prior probability of that particular class. So like this, you will find for each Vj, that is, say for class yes, we'll find this. Same way for class no also we'll find it. Then whichever is maximum, we'll take that. Okay, so let us just see an example. So usually if you see machine learning books or lectures, this is a typical initial problems which was discussed. Okay, so this outlook equal to different categories, temperature equal to D1, D2 are just days, it is not an attribute. So outlook has different values like sunny, overcast, rain, and temperature has they're all categoric. Okay, so temperature can be hot, mild, or cool. Humidity can be high, normal, or high or normal. Wind can be weak or strong. And then there is a class label whether that day they have played tennis or not. Okay, so it's a yes or no. Two class classification. So given this data set, okay, and we are having a what is that prediction to be made, that is outlook equal to sunny, temperature equal to cool, humidity equal to high, wind equal to strong. That is the instance given to us. We need to predict the label, that is whether the play tennis would be yes or no based on our naive Bayes classifier. Okay, so now for that what we do. So can you make a guess if you have not learned naive Bayes? If you have already learned naive Bayes, of course you would know it. Those who have not learned naive Bayes, can you make a guess? Because we already told, given the data set, we are trying to predict whether it would be yes or no. So first we will be finding, say, probability of play tennis equal to yes given this instance. So each attribute, okay. Same way, probability of no given this instance. So that's what we are going to find. So for probability of yes given this instance, how do we find, what is our right hand side? It is each attribute. So probability of sunny, comma cool, comma high, comma strong. Okay, sorry, probability of yes given sunny, comma cool, comma high, comma strong. That's what our input is. So how do we write it? It is equal to probability of sunny given yes into probability of cool given yes into probability of high given yes into probability of strong given yes. So can we try to find, I think if I show, it will all come together. So can we find, okay, I don't have a, I forgot to hide it and show. Okay, now can you find probability of sunny given yes? That is probability of outlook equal to sunny given play tennis equal to yes. Can somebody say me? The question is probability of, first of all, can you tell me what would be the probability of play tennis equal to yes? What would be the probability of play tennis equal to no? Can somebody say me? Unmute and say.
I'm 9/14.
Yeah, there are 9 instances with yes. So it will be 9/14 for, we are talking about the prior probability, or we can say probability of yes. Okay, we have 14 instances, out of which 9 of them are yes. So probability of yes is 9/14. Okay, now what about no? The remaining 5 are no. So 5/14 is our probability of no. Okay, now, sorry, my question is, given that it is play tennis equal to yes, what is the probability of outlook equal to sunny? You should tell me how you got it also. That is probability of outlook equal to sunny given the play tennis equal to yes. Can somebody say me? There are only 9 instances with yes. So how do you find it? You know that you have only 9 instances with yes. Now, given, because it is given that it is yes, so we need to consider the instances which are yes. Okay, in that, how many of them are sunny? That's what you're going to check. So denominator is 9. Now, so numerator, can you tell me how many instances with yes we have it as outlook equal to sunny? Can you count and tell me from the data set?
2.
Yeah, 2. So that means out of 9 instances where we had class label as yes, we had 2 instances where outlook equal to sunny. That's how we will find that. So probability of sunny given yes equal to 2/9. Now can somebody say me probability of temperature equal to cool given yes? How many? Yes, in the sense it's the class label or your play tennis. So probability of temperature equal to cool given S. Can somebody say me? Of course, denominator is 9 because we have only 9 instances with yes. Now, can you tell me the numerator?
3 by 9 or 1 by 3?
Yeah, 3 by 9. So we are just telling it exactly like that because we need to know. Otherwise, if you cut it off, we won't know how you got it. So 3 by 9, that is 9 instances where we have category as yes, your plate tennis as yes, out of which we had 3 instances where temperature equal to cool. Okay, so that is our probability of cool given yes. Now, what about the next parameter? That is probability of high given s. How am I selecting that? Because our last, if you see the instance where you need to predict, below this table you are seeing an instance, isn't it? This is the unknown sample. You're going to predict the label for it. That is, given a day, that outlook is sunny, temperature is cool, humidity is high, wind is strong. And you are asked to check, like before it actually happens, we are asked to predict whether they will play tennis or not. Somebody would play tennis or not. So for that, we are actually taking each conditional probability. Okay, first we are finding for yes. So now for that only you are taking sunny given yes, cool given yes, now high given yes. That is humidity equal to high given yes. So we know that we have only 9 instances for S, out of which how many are high? Humidity high. Is it difficult to count like this from the screen? There are 3 if you can count. Okay, so that is 9 instances with yes, out of which we have 3 instances where we have humidity equal to high. Okay, now we have last attribute, that is strong. So wind equal to strong. Given that it is yes, how many have wind equal to yes? So we just count, sorry, wind equal to strong. So again we count. So out of 9 we have 3. Okay, so that is 3 by 9. So if you see here, okay, so we are just, so the what we do is it is just the what is that formula application. So what I have written is, first we have to find probability of sunny, cool, high, strong given yes. Then I think I wrote it wrong, isn't it? Am I correct? What is our prediction? What are we going to predict? Given the data, what is the probability of yes? Isn't it? I wrote it. Is my sentence correct or wrong? The 2 lines just before the find max. Okay, just below our VNB, argmax of P of Vj, pi I, that I have written P of sunny, cool, high, strong, given yes. Is that the question? Is that what I have to predict?
No, ma'am, the other
No,
way.
it is the other way. So I made a mistake in writing. Sorry for that. So you should write the other way. That is probability of yes given sunny, cool, high, strong. Okay, same way probability of no given sunny, cool, high, strong. Okay, that is our prediction what we have to make. I'll rewrite and upload it again. Okay, anyway, I have not shared the slides. So it is the other way. So kindly excuse me. I think while writing I made that mistake. So now first you have to find the probability of it being, the instance being yes. Then we need to find the probability of the instance being no. Then we need whichever is maximum, that is our final prediction of that particular instance. So for that, for yes, we are trying to find, that is and we told all these terms no previously. The whole each of these multiply, I mean each of these should be multiplied, and of course you have to multiply it with the prior probability of yes also. So probability of yes, that is our 9 by 14, which we told earlier, into 2 by 9, which is our probability of sunny given yes, into 3 by, see, don't just copy from the notes. Okay, what if I have made mistake? So you also try on your own by counting after I give the PPT. You check whether it is correct, and then only you understand the concept. Okay, because when you get a problem, you should know how you are finding it. Each attribute for the yes category, each attribute conditional probability given it is no, we multiply them, and then particular class, that is if it is yes, probability of yes, or if it is no, probability of no, and then you get some value. So for yes we got a value 0.0053. Same way for no, we got a value of 0.02. 0.0206. Okay, now we should see whichever is maximum. So which is maximum? No or yes?
No.
No. Okay, so no is maximum, so we predict it as no. The plate NS is no. So that means the outlook is sunny, temperature is cool, humidity is high, and wind is strong. And we predict that plate NS, they don't plate NS. Okay, so this is how our naive-Bayes algorithm would work. Okay, is that clear in the steps? Do you have any confusion? This is our basic naive-Bayes approach. And see, when we say, actually it is sunny, cool, high, strong given yes. But then we are just multiplying sunny given yes into cool given yes into, that is in the bracket you are seeing, no, 2 by 9 into 3 by 9 into 3 by 9 into 3 by 9. That is possible because we have made an assumption that given the class, the attributes are independent of each other. So independent events, we just multiply each other to get the product. So, I mean the probability. So that's why we are just multiplying it. So this is the assumption what we make here. Okay, because of that assumption, we are just multiplying it. Okay, is there any confusion in that? The steps? Shall we move on to the next slide? Okay. So now, this is another data set. I think KNN, I told you I'll give you some question. No, I forgot to upload the slide. Okay, I'll upload. You can try that. Also, you can try this also. Okay, the same way. Okay. So do you remember me initially mentioning age actually a continuous value, but it can be a categoric value also, like in this example. See, if you see this example, you have three categories: less than 30, 31 to 40, greater than 40. So three categories for the age. So in this example, we can say age is a categoric value. Okay. So we have four attributes. So we have four dimension and we have one class, which is two class problem. And then a sample is given below. Like if in the last, if you see, age is a particular category, less than or equal to 30, income equal to medium, student equal to yes, credit rating equal to fair. So that is the instance given and we have to predict. So what we'll do, we'll first predict for the yes, Bayes computer. Oh, I think the table is not very clear. The attributes are age, income, student, that is whether the person is student or not, then credit rating, and then Bayes computer. So that is our final label or the class, Bayes computer, yes or no. Okay. So now for this particular instance, we need to predict whether the person would buy a computer or not. Okay. So you can just try that. Okay. Manually, like you have to try out as an example. Don't answer is here, but I'm not showing it. We'll discuss in the next class. I want you to try and come. Okay. Now, yeah. Somebody wanted to say something? No. I think somebody has unmute yourself. Okay. So now there is something called zero probability problem. That is, always, it is not necessary that we always get some value on the numerator. Okay. So sometimes, say for example, I have say 1,000 tuples. Okay. And or say, sorry, before that, I say I have say I am taking yes. Okay. Yes category. So in the yes category, maybe I don't have a value for income equal to low. Okay, so what do? So when we take the attribute conditional probability, we may get it as given Bayes computer equal to yes, probability of income equal to low would be 0 because it is 0 by something. Okay, now what do? Okay, so there may be situations like that where we don't have some value, some count for the instance. So then our probability becomes 0. But what happens, since we are multiplying all these, even if one of the attributes value becomes 0, the whole value becomes 0 because it's just multiplication, isn't it? Each attribute probability we are multiplying. So one of them becomes 0, everything, the whole probability would be 0. Okay, so what can be, we say it as Laplace correction. There are other methods also. This is a basic method what we do. So what happens is, assume that we have 1,000 tuples. Okay, so income equal to low, we don't have any. Income equal to medium, we have 990, and income equal to high, we have 10. Okay, so if that is the distribution, So now we know that income equal to 0 is our, income equal to low, we don't have any instance. So of course our probability would become 0. No, so now what we'll do, we cannot simply add 1. Now see, why we are doing this is like, we have say 1000 tuples. Adding 1 to it may not have much change. Okay. So what we do is, we add a 1 to each case. That is, we have 3 for this particular category. That is, say, income equal to low, income equal to medium, income equal to high. So for each of these category, when we find the probability, so it is added as 1 above. In the numerator, we are adding 1. So in the whole data set, we are adding 3, because each category we are adding 1. Okay, so that there is no change in the distribution. So relatively they're all added. Okay, so so income equal to 3 different categories. Each category we are adding 1. Okay, so income equal to low probability, when you find, it becomes 1 by 1003. Why it is 1003? Because we have added in each category. So low also we have added 1, medium also we have added 1, high also we have added 1. So we have 3 added together. So that's why our denominator became 1003. Previously, if we have not done this change, it would have been 0 by 1000. Okay, 990 by 1000 and 10 by 1000. Okay, that is now modified as 1 by 1003, 991 by 1003 and 11 by 1003. Why 991? It should be 990 by 1003. No, because in each category we are adding 1. Okay, just to maintain that count. Okay, there is some, if there is some distribution, we don't want to, of course there is a modification manually, I mean in the sense made by us. So there would be a slight this thing, but still, instead of the whole probability becomes 0 just because of an attribute, we make this kind of a modification. So it is called Laplacian correction, where for that particular attribute we increase whatever values we have. Like see here, we had 3 values for that particular attribute. So we add 1 instance for each of these attributes. Okay, so the count would be increased. So now it is like adding a extra instance kind of. So the count is increased by 1 for each category. So our numerator changes by 1 and our denominator changes by the number of attributes. So here number of values this attribute takes. So we have 3 values here. So it is 1003. Okay. So now we can say that corrected probability estimates are close. If you find 1 by 1003, it is like 0.00 something. So it's like almost 0, but then it's not 0. So we'll not have this issue of the entire probability getting cancelled. Okay, there are other methods also. This is like one basic approach what we use. Okay, so I think it's time. So we'll stop here. I'll try to upload this question as well as this particular question. Also, I will try to upload KNN. I think one question I wanted you all to try. So those two will sorry, I'll upload. Okay, and then you can try on your own, and if you find any difficulty, we'll discuss in the next class. Is that okay? Are you all here, or it's just me and Bina ma'am? Somebody is here? Yes.
Yes.
Okay. I think your CRs would have what is that, circulated the form, right? Hope you all have filled your teams. Tomorrow morning we'll freeze it, and then we'll see if there are people who couldn't form groups. We'll find out. There were multiple requests like 6 in the team, etc. I don't think I can allow many of you to have 6. So as of now, assume that it is only 5 in a team. So form it. If you don't want to form it, we'll make the teams, and then we'll finalize it in a day or 2, and then meanwhile you start searching for the data set. Bina ma'am, I have given this instruction in our previous lab.
Okay, fine.
So few of them wanted to form their groups on their own. So I told they can do that. So the rest of them who don't want to form, we can just assign based on the register number or something. So likewise, 5 in a team, we'll form groups, and then they'll start searching for the data set. And when they come to the next lab, by then they'll be clear with the groups and the data sets.
And okay, fine, no
In
issues.
the next lab, we'll just see through their each of the team, like what problem, I mean, what data set they have taken, where they have taken, etc. So we'll have a rough idea on like whether it's fine, etc. So that later we'll not have issues.
Okay, fine.
Okay, ma'am. I think that's all from my side. We'll end the session.
Yeah, fine. Bye.
Okay, ma'am. Okay, students.